Hey guys, welcome back to another session, which is probably going to be the last session that we have of the CCNA video series. And I hope you all are doing good there. That's a great effort, Nelson. You joining the session pretty early in the morning. I hope, however, this training has been informative for you. But yeah, this is going to be, yeah, I know. All right, let's get started with what we need to discuss in this training. So we're going to start our day, or we're going to start our session by discussing STP, okay, which is a pretty important topic in the whole CCNA studies. So STP, as you all are aware, stands for Spanning Tree Protocol. Right? It stands for Spanning Tree Protocol, and it's one of the key components, or you can say one of the key protocols that you need to be aware about. Okay, it's quite complicated to understand, and the more you dig deeper into, the more you explore about it. Okay, there is a lot to study about Spanning Tree Protocol when you actually discuss about it. So we are just going to get a glimpse of how Spanning Tree Protocol actually works, and I'm gonna throw you the knowledge that is actually required for you to complete your CCNA studies. So what I'm gonna do is I'm gonna draw a topology. That topology we will kind of consider and we will use in order to understand how STP operations gets conducted inside a switching environment or inside a layer 2 environment. Okay, so as you might have done Google for quite a lot of times, that what is STP, you might have heard about STP as well, that it is used, or it is by default used on devices in order to avoid the layer 2 loops, right? Just a minute. All right. So we are going to discuss about the same, which is Spanning Tree Protocol. And in this Spanning Tree Protocol, there are quite a lot of small things that you actually need to understand. And you need to make sure that you understand how switches actually behave. So when I take a topology in a way, for example, I'll draw something like this. Let's say that we have a couple of switches there. For example, you have a switch like this, which is your switch 1. Then you have switch 2, and then you have your switch 3. Okay, and then you connect these devices like this, and there are different ports as well that are going to be used. So your switch 1 is using FA0/1, and then FA0/2, and then let's say FA0/1 and FA0/2 and FA0/1 and FA0/2. These are basically the ports that are going to be used, or that are being used over here. Okay. Now, when we look at the topology over here, you need to understand how layer 2 loops actually forms. And STP actually is a complete layer 2 protocol, okay, because it functions with the layer 2 devices. It also works with layer 3 switches, but you can consider it as a layer 2 protocol because it completely takes its decisions based on the MAC addresses and some other parameters as well, but not on IP addresses. So that's why it's a layer 2 protocol that you can consider it as. So when we look at this topology, there are certain things that comes into this topology. Let's say that you have a device that is connected over here, and that particular device is actually connected to FA0/3 port over here with the switch one. Okay, and then there is another device that is connected with the same switch on FA0/4. Now currently the switch has just turned up, okay, and it doesn't know about any of the MAC addresses that are there, that are present into the MAC address table, because the MAC address table is clean and it doesn't have any of the information present over there. So what's going to happen in this particular case is, whenever the communication needs to be done from this PC to this PC or from this PC to this PC, then any one of them are going to initiate a transfer. Let's say the first PC initiated a communication and that communication reached out to the switch. Makes sense? Now, when the switch is going to receive this part of communication, then switch is going to look into its MAC address table, right? And in this MAC table, it will find the information that does it know about the MAC address that it has. Let's say that the first PC has a MAC address of AA and the second PC has a MAC address of BB. But currently, it's not going to have any information about the interface and about the MAC address inside its MAC table, right? And what's going to happen in this particular case is, as soon as the switch receives that particular traffic, then it's gonna embed the information that is present into the source MAC address field into the MAC address table. So as the traffic is being received on FA0/3 port, it's gonna say that FA0/3 is connected with a user that has a MAC address of AA. But that user is intending to go on a destination MAC address of BB, but I do not have that information onto my MAC address table. Now, in that case, what will switch do? We just discussed yesterday about what will switch do in this scenario. Can anyone guess that? I told you a term in the previous video, or like a couple of videos back, that how switch is going to respond this particular traffic. The switch is going to initiate something called unknown unicast forwarding, right? Unknown unicast forwarding or unknown unicast flooding, you can say. And in that particular scenario, what's going to happen is switch is going to forward a copy of that particular frame upon every port that is present, except the port that it received the information on, which means it's going to forward the traffic, the same traffic on FA0/1, 2, and 4, asking out that, hey there, is there anyone who has a MAC address BB? And then switch B is going to respond to that particular message saying, hey there, I am the one who is having the MAC address BB. And then switch is going to add an entry that FA0/4 is connected to user having a MAC address of BB. And then the packet which it holded will be forwarded over here. Do you understand this? Perfect. Now, this is one aspect of what's going to happen inside of the switch. But what about the packets that were actually forwarded onto the other interfaces, which were FA0/1 and FA0/2 of the switch? In that particular scenario, when FA0/1 forwarded the traffic, it received it was sent out on FA0/2. And then the FA0/1 traffic was also sent out on this particular switch. And how did these switches responded to them? It's possible that the switches are also connected to some end users like this. Okay, they have a user A, B, C, and D. And switch 3 also has some users like X, Y, and Z. You can consider that, right? So how the switch is going to react to the unknown unicast flooding that is going to receive. Okay, what's going to happen in this particular scenario is the switch is also going to forward the traffic on all of its ports. Okay, so it's going to forward the traffic on this, on this, on this, and also on this as well, and it's going to forward the traffic on this interface as well. Do you understand that? Now you would say that maybe you told me that uh, the switch is not going to forward the traffic on the interface upon which it received the query from, or upon which it received the content from, right? Or the frame from. Now you see, the traffic that the switch is going to forward to switch 2 for asking whether is there any destination host that has a MAC address of BB, it's not the original frame, right? It's the copy of that particular frame. And the original frame was received on FA0/3 of switch 1, not on FA0/2 of switch 2. That's why the switch 2 is going to forward that traffic out on FA0/2 as well. Do you understand this? Makes sense to you what I'm talking about? And that's exactly what's going to happen over here as well. So when you look at switch 2 is also going to forward the traffic, but switch 3 again is receiving that same traffic from switch 1 as well, and it's going to forward that particular traffic over here, and it's going to forward that traffic it's going to receive over here as well. Okay, and over here as well, and over here as well. So what are these traffics? These traffics or everything when the traffic is actually revolving from one way around, okay, or it's the other way around as well. You see, there are loops that are forming up, and these loops are called as layer 2 loops. Now if you look at the perspective that you might have a question in your mind that whether, like, what is this unknown unicast forwarding? Is it same, like it's same, like it does sound same like something like broadcasting, right? But broadcasting is different, and unknown unicast flooding is different. When we talk about unknown unicast flooding, then there is no destination IP, or sorry, destination MAC that is associated with it. The switch just forwards a copy of that particular frame on every port that's there, okay, using the base MAC address of it. But when you talk about broadcasting is an intended forwarding. It doesn't forward a copy of that particular frame. It forwards the exact, like it forwards the frame itself onto the network, and the destination MAC will be all Fs into the destination MAC feed, like that. Do you understand what I'm trying to say? So that's the difference between your unknown unicast forwarding and broadcasting. So it creates loop that actually can cause various other problems to your network. Okay, it creates various other things like broadcast storms. It consumes unnecessary bandwidth, a lot of unnecessary bandwidth utilization that happens there. And there are certain other things as well, which causes your network to come to a standstill. And in order to avoid such loops from getting formed, STP comes to your rescue, which is spanning tree protocol. Okay, now do you understand the purpose of why we actually use spanning tree protocol? And these things are also used for security perspective as well, but you will get to know about them into your CCNP studies. Okay, now as we are done with the motive of knowing spanning tree protocol, that why it is there in place, because you do not have to configure it manually. It's already there in place, and yeah, you just need to know about it, that how it works, and you do not really need to mess up the configuration or whatever configuration that you're allowed to do onto STP. You really need to be good with it. Otherwise, don't mess with it. That's what the simple rule is. Okay, otherwise you will kind of like bring your network to a halt if you play with STP and you do not really know what you're doing. Okay, So let's talk about how STP actually works. Give me a minute. I'll have a sip of water. Yeah. So let's talk about how the things works in STP. Now I'll clear up the topology. And I will draw the topology again, which we are going to talk about spanning tree protocol. Then we're gonna again have the same set of switches. You have switch 1, then you have switch 2, and then you have switch 3. The switch 1 is connected like this, switch 2 is this, and switch 3 is this. Your interfaces are FA0/1, you have FA0/2, FA0/1. There you go. These are the interfaces that are actually there. Okay, now we are considering this scenario. You need to understand that STP will only work completely whenever there is a redundancy in your network, which means you have a network that actually has the ability to reach out to the same destination by using two paths. Okay, for example, for communication between switch 1 and switch 2, you can go from here as well, like by using the first link as well, like from here, and you can go from here as well, and you can do like the same thing in order to go from anywhere to anywhere in this particular topology. That's why STP actually needs to be there. Now STP does the work of avoiding loops or stopping the loops from getting formed by using some elections. So there is a certain process that is involved that you actually need to know in order to fully understand how actually STP works. So it all starts with something you can call it as something that refers to as BPDU exchange. So the first process that is involved into your STP or into your spanning tree protocol is BPDU exchange. Okay, bridge protocol. BPDU actually stands for bridge protocol data unit. Okay, and this bridge protocol data unit contains something called BID, which is called as bridge ID, and the content of that bridge ID is priority value plus the MAC address. So the priority value is of 2 bytes plus the MAC is of 6 bytes, which is 48 bits, and totally the content of the bridge ID is, you can say, 8 bytes. Make sense? That's how bridge ID is actually built up of. It will contain a priority value and it will contain a 6 bytes of MAC address, and combining them together, you will like get something called bridge ID then. Cool. Now this BPDUs, which is bridge protocol data unit, is actually exchanged by every device that is available there, and by default the priority value is set to 32,768. By default, it will always be same 32,768. Plus, it will also have a system ID extension with it, which is going to be the VLAN ID as well. Okay. So right now we will assume that every switch has a default priority value. So that's gonna be 32,768 on switch 1, 32,768 on switch 2, and 32,768 on switch 3. Then along with that, the switches also have some MAC addresses, considering the first particular device, or you can say switch, has a MAC address of 1111:1111:1111. Okay, we are not going to write down a full-fledged 48 bytes or 48 bits of address. I'm just writing a 3-octet address, which is made up of, you can say, 16, 12, 12, 12. That's around, what's 24 bits? Yeah, 24 bits of address. And then you can say 2222:2222:2222. And then for the third one, it's going to be 3333:. These are the addresses or MAC addresses that you have. Now, what's going to happen in this case is as soon as the switch boots up, it's going to exchange the BPDU. Okay, and then the switch 2 is going to receive that particular BPDU there. Now, when switch 2 receives the BPDU, then in that particular case, the BPDUs are considered as of two types. The BPDUs can either be superior or they can be inferior. You can have a superior BPDU and you can have an inferior BPDU. Now, what is superior and what is inferior BPDU? Whenever a switch receives a BPDU, it compares the value of the priority with the priority value that is compared on the local switch, which means when switch 2 is going to receive that particular BPDU, switch 2 is going to check the priority value of the incoming BPDU, and it's going to compare it with its own BPDU. And what's going to find? It's going to find that the priority value on both the switches is actually the same. Okay, so based on that, it cannot decide whether it's a superior BPDU or it's an inferior BPDU. Then, if the priority value is like tied up, then the tiebreaker is MAC address. Okay, so the next value that actually will be considered over there is going to be MAC address, and then the incoming BPDU's MAC address will actually be compared with the self MAC address that's present onto the receiving end switch. And then in that scenario, the switch is going to find out that the MAC address of the incoming BPDU is lower than the MAC address of the local switch. And that's why whenever you have a winning value, or whenever your priority or whenever your MAC address is lower than the local MAC or priority that is present onto the switch, the BPDU will be considered as superior BPDU. Do you understand that? I am again repeating that. Whenever the priority value and the MAC address is lower in the bridge ID, or whenever these values are lower than the local values that are stored, then on that note, you can say the BPDU is considered as superior, which means winning BPDU. And if the value is not lower than the local value, then it will be considered as inferior BPDU, which means a losing BPDU. Do you understand both the terminologies of BPDUs? Perfect. Now, in the same scenario, what's going to happen in that case then? Whenever the switch 2 decides, whenever the switch 2 decides that the incoming BPDU is superior, then it's going to assume switch 2 as its root bridge. Okay, so what's going to happen that all the switches are going to exchange this BPDU with each other, and whenever the complete exchange is done, then the outcome of that particular thing, let me clear this thing up, and let me tell you that the outcome of this particular scenario is going to be something that election of root bridge will happen. After doing BPDU exchange kind of helps you to come to a conclusion of root bridge election. Makes sense to you? It happens like over there. So whosoever has the lowest MAC address, or if the MAC address like whosoever has lowest priority, and if the priority value is same, then whosoever has the lowest MAC address will actually win that election, and that switch is going to become a root bridge. Now in that scenario, or in our scenario, who will become the root bridge? Can I say that root bridge is going to be switch 1? So I can say this particular scenario, or this particular switch becomes a root bridge there. Okay, that's the election. That's the first election that happens in STP. Then after that, the next election will actually happen in order to select a root port election. Okay, root port election will actually happen, and the root port election will be concluded in order to find out the shortest path on every non-root bridges, which means who are the non-root bridges that we have? We have switch 2 as our non-root bridge, and we have switch 3 as our non-root. So both of these switches need to find out the shortest distance that they have, or the interface that has the shortest distance in order to reach out to the root bridge. Okay, now how would it be calculated? Now in our scenario, what's going to happen? What is going to be the root port for switch 2? Which means which port does reaches out to the root bridge in the shortest distance possible on switch 2? Can I say that FA0/2, like this particular port, has the ability to become the root port? And in our switch 3, FA0/1 needs to become the root port. Right? Now consider one thing. As of now, all of these links are basically using fast Ethernet links. Right? Because what's going to happen in that particular scenario is currently switch 2 has two ports, FA0/2 and FA0/1. If it uses FA0/2 reach out to the root port, it reaches out to the shortest distance possible. If it uses the other way, then it needs to cross one hop that actually creates delay, or that's actually a longer distance route than the current one. Okay, so over here, what's going to happen if I have this particular link as 100 MB link, which is a fast Ethernet link, and then I have the other link as gigabit Ethernet link, which is like 1 Gbps link, and this link also is 1 Gbps link. Now in that scenario, which particular path is the shortest distance? Even like if you look at the configuration, then can you judge? Then you can actually make sense that when I send traffic from over here to over here, then my traffic has more likability in order to reach out to the root bridge in the fastest way possible, because the other route is actually using the root port. The other route is actually using the 1 Gbps link, and the shortest path, or you can say the lesser distance path, is actually using 100 MB link. Now, for considering the same thing, there is something called port cost values. and there is a fixed value that is given to every type of port that is out there. So if you have an Ethernet link, then the cost of that particular link is going to be 100, and this is fixed cost. Okay, you cannot change the cost of that particular link. If you have a fast Ethernet link, okay, then the cost of that particular link is 19. If you have a 1 Gbps link, then the cost of that particular link is 4. And if you have a 10 Gbps link, then the cost of that particular link will be 2. Now, considering the same thing, when you look at the example over here, then you get to know actually that if you use 1 Gbps over here, then the path cost is just 4 and 4. And when you use the 100 Mbps link over here, then the path cost will be 19. Which means that if I send traffic from over here to here, then the cost is 19 to me. But if I send traffic from the other way around, then the cost is 4 plus 4, which is 8, which actually is lesser than the cost of 100 Mbps. And based on this information, it gets able to decide that which port reaches out to the root bridge in the shortest way or the fastest way possible. And according to that particular calculation, it decides which port deserves to be root port on my local switch. Do you understand what I'm trying to say? Perfect. So that's what the second election is. And root port, your every switch who is not a root bridge will at least have one root port. Okay, it is mandatory to have a root port onto your switch. Okay, but that switch, like, there won't be any root ports onto the root bridges because the switch itself is a root bridge, so it doesn't need to reach out to any of the other root bridges. Okay. Yeah, so that's the third step into our spanning tree protocol. Let me erase the topology over here, and then we'll move on with the next election. So as of now, what has happened is you have been able to decide which port or which switch is going to be the root bridge and which port on every non-root bridge is going to be the root port. And the conclusion was, considering that all of the links are FA0/0, we have FA0/2 of switch 2 as the root bridge, and then we have FA0/1 as the root port, not root bridge here. Okay. And then if you talk about the other links that are available there, which is FA0/1 and FA0/2 of the root bridge, these ports will be awarded with something, or will be called as something called designated ports. And designated ports are basically the ports that are designated which will never go down. Okay, they will be into forwarding state. Make sense? So any port of the root bridge will never go down. That's why all the ports of the root bridge will be like given a name of designated port there. You get that? And then the only thing that is remaining here to understand is FA0/1 and FA0/2. These two are the ports that you actually need to decide which one will become up and which one will become down. Because ultimately, spanning tree protocol is actually something that does the job of blocking a specific port so that loops can actually be avoided. So physically your topology will be like this only, but logically your topology is going to be something like this. So you have your switch 1, you have your switch 2, and you have your switch 3. Okay, you won't have this link. This particular link is going to go down because in order to avoid the loop. Okay, so out of this particular logical like physical topology that you have a connection between switch 2 and a connection between switch 3, which port will stay up and which port will go down? This scenario also is actually decided by considering the upward link, which means whenever your switch 3 or whenever your switch 2 actually needs to decide that whether FA0/1 is going to be blocked or whether FA0/2 is going to be blocked of either switch 2 or switch 3. Okay, this decision is taken by considering the uplink MAC address, which means that switch 2, like it will be considered that whosoever has the lowest MAC address will have its particular port up, and the other particular port will be going down there. Meaning that which particular port will go down here? FA0/2 will go to blocking state because the MAC address is higher there. Okay, and FA0/1 will be awarded as something called designated port. Do you understand that? That's the process number 4 of electing the STP routes. So you can say that blocked port election. Okay, block port election is actually done like this. Again, I'm repeating that because switch 2 has lower MAC address than switch 3, that's why switch 3's port will go down and switch 2's port will go up or will be up. Now, you might have a question in a way that why the port will stay up if the link is not going to be used. Let's assume that this particular link goes down. And when the link between switch 1 and switch 2 goes down, then in that case, switch 2 will actually need to notify the other end as well that, hey there, my primary link has gone down. Please turn yourself up so that I can forward traffic by using this link. But if I put both of the links as a block port and block port, then the link will never come up until unless a manual interaction will actually be done there. So that's why, that's why you can say that the designated port kind of acts as a backup port as well, or like upon need, whenever there is any need, then the port will actually tell the other end of that particular link to turn itself up and start forwarding the traffic. Do you understand what I'm trying to say? Perfect. Now, after discussing this process, you actually also need to know about something called port states and about something called Stp timers. So there is something called Stp timers as well, but I'll write it down into a different marker. Let's say this. You have Stp. Oops, that's pretty blank there. So you have Stp. Oh, what happened? Stp timers. The first time is actually hello time. The second time is actually forward delay time, or I will write it completely. Forward delay time, and the third time is called as max edge time. Now, hello time is of 2 seconds, forward delay time is of 15 seconds, and max edge time is of 20 seconds, which means that the BPDUs will keep on exchanging every 2 seconds. Okay, 2 seconds here, 2 seconds here, 2 seconds here. Every 2 seconds, the BPDUs will keep on exchanging. Okay, until unless BPDUs is not sent, the link will not be treated as up. This is like just like the EIGR for OSP of hello packets that they exchange in order to identify whether the neighborship is up or down. Okay, just like that, you have STP BPDU hello packets that actually are exchanged every 2 seconds between the switches that are there connected with it. Make sense? Then forward delay time is something that for that you actually need to know about Stp port states. So by default, the port is into disabled mode, which means the interface is actually down. As soon as it goes up, then it goes into a state of listening. So you can call it as listening mode, and then it goes into learning mode, and then it goes into forwarding mode. And then after that, it also has a blocking mode as well. These are the 5 states that are there in a switch port that you have. Now, what does disabled means? Disabled means that if your port is physically down, then the status that it's going to have is disabled. Then as soon as the port comes up, it goes into listening mode without waiting for anything. And then in listening mode, it participates into BPDU election. It doesn't do anything apart from like participation into the root bridge election or BPDU exchange process. It only does exchange BPDUs. Okay, it will not be able to forward the traffic. You see, whenever I put a switch there on my topology, and if I turn on that particular switch, that switch goes like that switch makes its port from red to amber, and then from amber to green. So the time taken from that, or the time taken for that particular convergence is actually considered something as Stp convergence time. And when the port is actually not green, it means that it's going through Stp calculations. Okay. So as soon as you turn up the port will actually go orange or amber, and then it will transition into listening mode, where it's just going to learn, or it's just going to participate into BPDU exchange process. Then after that, after forward delay time, which means after around 15 seconds, it will transition into learning mode. And in the learning mode, it continues to exchange the BPDU packets, but then it also starts learning about the MAC address, which means it starts building up its MAC address table there. You understand that? And then after that, another 15 seconds will be passed, and then your port goes into the forwarding mode, where it does the all operations of exchanging the BPD. It also keeps learning the MAC addresses, and it also starts forwarding the frames there. You get that? And then after that, the port will actually go into that. If you do not receive the hello messages for 20 seconds, or the BPD packets for 20 seconds, then the port will actually go again disabled, or it's going to go blocked, depending on whatever scenario is true to that particular thing. So maxage time is actually the time that will be considered in order to announce an interface is down, and that link no longer needs to be used, and you can look for the alternative links. Make sense? So whenever you create a topology, that's exactly why we say that the Stp topology can take up to 30 seconds to convert, which means because the port actually goes from dual 15-second transition, and after 30 seconds, after it reaches out to the forwarding mode, then it will be able to forward the traffic. Until then, it won't be able to forward the traffic. Do you understand this? And there are other features here that are available that you can configure port fast and everything else. Whenever you configure port fast, then your port directly or only stays in forwarding mode or disabled mode, because it doesn't participate into the BPD election. It doesn't participate, or it doesn't participate into the STP process at all. STP is disabled on a port that actually configures itself with port fast feature. And port fast is actually enabled in order to secure your layer 2 network. You can configure port fast by using switch spanning tree port, by going into the interface and saying spanning tree port fast. Okay, we'll be talking about that, however, but this was the basics, and this was kind of the understanding class of how spanning tree actually works. Make sense to all of you? Perfect. All right, we'll take a 5 minutes off there, okay, or 10 minutes off, and then we'll move on to see how STP actually works. I'll show you a topology, and in that particular topology, you'll be able to identify how STP actually works. Okay, thank you so much, guys. I'll see you in around 10 minutes. Thank you. Hey guys, I'm back. Sorry for the delay because I got an important call, so I had to take that. Yeah, so moving on, we're going to talk about the STP's operation, and I'm going to drag a topology here, and we'll see how that topology actually can like works. So I'm going to select a couple of switches or three switches over here. This is our switch 1, then we have our switch 2, and then we have our switch 3. I hope I'm audible to all of you. And then I'm going to connect the switch 1 with switch 2, and then the switch 2 with switch 3, and then after that I'm going to connect the switch 3 with switch 1 there, right? And you can see the interfaces are being used accordingly over here. And what we're going to do is, you see the lights are amber, they are not green yet, because that's STP convergence that's actually happening. The network is being converged, it is not converged yet, and after some time it will become green. There you go, the ports have started to become green now, and one of that particular port is going to be the blocked port, and the other port will actually be the active ports, and they will turn green. And there you go, completely the topology has been converged. This port is green, then the other port over here is again green, and then that's another green and green. But you can see that this particular port over here is it's still in amber mode, which means this is a port that is basically blocked by STP in order to avoid the loops. Okay, now what you can do, we're going to go on to every switch there, and we're going to rename those switches as switch 1, switch 2, and switch 3. So I'm going on to the CLI of this switch, and I'm going to say enable conf t host name switch 1. Okay, then I'm going to go on to the second switch to the CLI, and then say enable conf t and host name switch 2. And then I am going to go on to the third switch CLI and say enable conf t and host name switch 3. There you go. That's how we have renamed these switches. And now if I check the switch 1, what I can do is I can perform a command called do show spanning VLAN 1, because currently we just have VLAN 1 with us. Okay, or if we even say do show spanning tree, then it's gonna give you the same output. And you can check that the spanning tree protocol that is enabled is IEEE, which is a standard protocol, not a vendor proprietary protocol here. And then this information is actually the information about the root bridge. Okay, so root ID means who is actually the root bridge. And the priority value of the root bridge is this, the MAC address of the root bridge is this, and it says that this bridge itself is the root, which means our switch 1 is acting as the root bridge in our topology. Okay, maybe because it has the lesser MAC address, you can see that the MAC address, and this is basically the local information of the switch. So the first section gives you the information about the bridge, the root bridge, and the second information will actually give you the information about the local switch. So the local switch has a priority of 32.769, and the address is, the MAC address is this. These are the hello, maxage, and forward delay times, and the aging time. Aging time and maxage time is the same thing. That's kind of a thing that you would see into the old operating systems. And these two are the ports that you have. 0/2 and 0/1, and you can check the role of them are designated, and the state of that particular role is forwarding. The cost, because it's a fast Ethernet port, is 1990, and the type of the interface is point to point. Makes sense? That's how it works there. Then if we look at the second switch, if I go on to the second switch and say do show spanning, there you go. You also see the information that this is the information about your root bridge, and the priority of the root bridge is 32.769. Again, MAC address is same. The cost in order to reach out to the root bridge is 90, which means what is the cost, what is the link cost from switch 2 to switch 1. Makes sense? That's the information that is there as cost. The port number that is basically connecting with the root bridge is FA0/1. Okay, and the hello time, access time, and everything is same there. And this is the local switch information. You can see that 000 is less than 006. That's why this switch didn't win the STP root bridge election. You get that? And then you can check that FA0/1 over here has a role of root bridge, root port. And then FA0/2 is in designated mode, but the state of that particular also is forwarding, which means both the ports are capable of forwarding the traffic. You can see over here FA0/1 and FA0/2. You get that? And then if I go on to the third switch and check the do show spanning, there you go. The same information is there for the root bridge and then the local switch. And this also doesn't win the root bridge election because the MAC address of the switch number 3 is greater than the MAC address of the switch number 1. And the interfaces that are there over here, you can see that FA0/1 and FA0/2. Okay, so out of those, only FA0/2 is in forwarding mode, which is basically the root port, and the other port, which is FA0/1, is into blocking mode. Okay, that is not forwarding the traffic, and you can check that in the topology over here. FA0/2 is the port that is actually being used, and FA0/1 is not being used over here. Makes sense? This is how actually STP works. Any questions? Yes, also you can change the priority. So let's say that it's something required that there is a layer 3 switch that is being placed over here. And in the layer 3 switch environment, what you actually require is your layer 3 switch wants, you want your layer 3 switch to act as a root bridge. And you don't want the switch that just has a lower MAC address to become the root bridge. So in that case, you can actually decrease the priority in order for a switch to become a root bridge manually. But there is a condition that the priorities can only be set into the multiples of 4096, which means you cannot go and set the priority of this particular switch by saying priority as 100. That's not going to work, because by default every switch has a priority of around 32768, 32768, and on the first switch as well you have 32768 as a priority. But the priority that is being set needs to be in the multiple of 4096. So you can set it to 4096, 8192, 12,000 something, 16386, 20,000 something, and so on. So, okay, in the multiples of 4096 only. So let's assume that I want my switch 2 to become the root bridge. Then how would I do that? So what I can do, I can go to switch 2. I can say spanning tree, and then I can say VLAN 1, and then I can say priority, and I can change this priority between 0 to 61,440. But you can see bridge priority in the increments of 4096. So if I say bridge priority is 100, that's not going to work. Bridge priority must be in the increment of 4096, and the allowed values are 0, 4096, 8192, 12288, 16384, 2480, and so on. So I can say something like priority value, set it to 16384. And once I set the priority value of this particular VLAN or spanning tree to 16384, then I can check show spanning. And you see, this particular switch has become the root bridge now, and all of its ports has become or went into the designation mode. or the designator mode. And then you can see that now the blocking port will actually change. It's actually transitioning. It takes time for STP to make the changes. So when I go and say, there you go. Okay, now the blocking port is different. Makes sense. If I go ahead and if I kind of change the priority to 0, that's also allowed value. Okay, there is nothing specific about that. But then this particular port who has 0 as the priority will again when the lowest, it will act as the lowest one, and no one can win the root bridge election over it. So you can set the value to 0. That's not a problem. Okay. Then after that, let's say that you have a PC that is being connected over here. And in that particular PC, whenever you kind of make a connectivity with that PC, over there, you can see that FA0/3 now is being connected with switch 2. And if I say show spanning, there you go. The port is in listening mode now. That's the new port which is actually being connected with the PC. And then it will go to from listening. There you go. Now it went to learning. And after some time, it will go to forwarding. Still in learning mode. Learning, again learning. And there you go. Now it went to forwarding mode. Which means that any endpoints that are actually being connected, they have something, or they also participate into STP election. But this is kind of vulnerable to your network. Why is that? Because it's possible that there is an attacker that is being connected to your network. Okay, and tell me one thing: if this particular PC uses, or this particular PC is being used by some attacker, and that attacker uses like a Kali Linux machine or something like that, and then he gets able to send a BPDU by using like a crafted packet, and he sends up a BPDU packet out on this link having the lowest priority possible, like priority 0, and its MAC address is also lower than the MAC address of the switch there. Then what happens? This particular PC will act as the root bridge of the entire topology, and he will be able to manipulate the entire layer 2 network according to its convenience. Do you understand what I'm trying to say here? So to avoid certain things, or to avoid such kind of scenarios, we actually put the ports that are there, which are connected to the endpoints, as port fast. We configure the port fast feature onto the endpoints port, so that the ports or the STP negotiations doesn't occur onto the links that are connected to endpoints. And how do you configure that? You can directly go into the switch, and you can select the interface by saying interface FA0/3, and you can say switch port spanning spanning tree, yeah, spanning tree port fast. That's basically the command. And when you say spanning tree port fast command applies, it gives you a warning that port fast should only be enabled on ports connected to a single host. But yeah, port fast has been configured successfully. Okay, but will only have effect if the interface is in non-trunking mode. Okay, which is the case we have. So that's how you configure port fast, and there are other features as well that comes into like STP security and STP others, which actually are considered when you talk about root guard and loop guard and BPDU guards and others as well. But that's enough more concern as of now to get to know about that. And I would say these terms you will learn about like loop guard and BPDU guard and root guard and all those things into STP security or layer 2 security in CCNP. Okay, so that was all that we actually had to discuss into STP, and then we will move on with the next topic that we have to cover, which is about access control list. So yeah, let me just clear the things up. There you go. I hope you all can see my screen now. Just a minute, please. Yeah, hey there. I am. So we are going to discuss about the next topic, which is access control list. Another complicated topic in order to implement, not to understand. In terms of understanding, it sounds pretty simple, but when you actually implement it, then there are a lot of complications and a lot of factors that actually need to be considered when configuration comes into play. Okay, so what's access control list? Assume that you have a scenario in which you have a router over here, and then you have another router over here as R2. And then this R1 is connected to some network, and R2 also is connected to some other network here, like this. And let's say you're using 192.168.1.0, and then you have 192.168.2.0 over here. And then you also have 192.168.3.0 in this. And then you are implementing, let's say, RIP, routing information protocol. Now, in this scenario, the communication between both of the networks are possible, right? Because routing information protocol is in place. Now, when you look, just a minute. Yeah, so when you have both of these networks that are connected, and you can say that 1.0 and 2.0 can actually communicate together. But you want certain host, or you want an entire network if you even have like an R3 there. And then that R3 also has a certain network, let's say 4.0 and 5.0. And you don't want this network to communicate with this network, or you don't want certain hosts to not be able to communicate with that one. So you can do traffic filtering by using access control list. The name itself signifies that it actually is about controlling the access of the endpoints with the other endpoints that are available there. Make sense? Now there are two type of access control lists that are available. Okay, one, there is a standard access control list, and second, it is extended access control list. Okay, the standard one, however, just blocks every type of communication from the source to the destination, no matter where the source is coming from. It's more inclined towards the destination network. It's more inclined towards on which device is it being applied. Okay, wherever Extended access control list kind of gives you a granular control that by using which you can actually control that if you want certain like protocols to be blocked, if you want certain port numbers to be blocked, while allowing the other ports for the same set of hosts and for the same set of endpoints. Possibly, let's say you don't want your you don't want your people that are connected in your enterprise network to be able to telnet to a specific router, to be able to telnet to the management network. Okay, but you want the data to be sent to that particular same network then. So you can block a certain amount of ports by using extended access control. It gives you like better control on what should be the source and what should be the destination. You can be more specific towards creating your extended access control list. However, in standard access control list, it's just about blocking a certain type of communication by considering the IP addresses for the destination network, and on whatsoever device you're going to configure them, it's going to apply that particular access control list to the networks that it's connected with. Make sense what I'm talking about? Perfect. Now, in that scenario, we're going to implement an access control list, like a standard access control list, and we're going to see how we can actually use it in terms of configuring it. So I'm going to create a topology, which is just going to be a small topology like we have been creating by taking a couple of routers over here. That's PT routers. And then I'm going to have a couple of switches as well. And I'm also going to have a couple of PCs there. And then I'm going to connect them together. Exactly like that. And you can say that the networks that we're going to have here. One 192.168.1.0/24. Then you have 192.168.2.0/24 and 192.168.3.0/24. Okay, now what I'm going to do, I'm just going to implement normal routing over here, and then we'll see how the configuration actually works. So I'm going to go on to my R1. I'm going to name this particular device as hostname R1. Then interface FA0/0, no shutdown, IP address 192.168.1.1 along with 255.255.255.0. Then IP DSCP pool A, network 192.168. 1.0 along with the subnet mask, and default of 192.168.1.1, and take an exit. And then interface SC2/0, no shutdown, and then IP address 192.168.3.1 along with the subnet mask. Right? And then I'm gonna say router rip version 2 and network 192.168.1.0 and 192.168.3.0, and that's all that you need to do on R1. Okay, then I can go on R2 and go to the CLI and say no, enable conf interface FA0/0, no shutdown, IP address 192.168.2.1 along with the subnet mask, and IP DSCP pool B and network 192.168.2.1, 2.0 along with the subnet mask, and default of 192.168.2.1. Okay, and then interface SE2/0 and say no shutdown, IP address 192.168.3.2 along with the subnet mask. And then if I take an exit and say router dep version 2, network 192.168.3.2 along with the subnet mask. Oh, sorry, this is just 192.168.1.0. Not 1.0 as well, 2.0. What happened to me? 3.0, and take an exit there. And then if I check the routing table on R2, oh, I didn't even rename this router. Say hostname R2 and say do show IP route. There you go. You have the route that has been exchanged and you have all the routes that are present there. I can go on to the first router and I can also confirm the same by saying do show IP route. And there you go, 1.0, 2.0 and 3.0, it's all present there. Make sense? Now, what I'm going to do, I'm going to go on to the PCs and I'm going to configure the IP addresses onto the DHCP. Blah. And go to the next PC and configure the IP there. IP config DHCP. Requested. There you go. It's done. Then I can go on to the third PC and configure an IP address of probably the second network that we have. Go to desktop, IP config and DHCP. And it should be that taking that time. Successful. Okay. Then I can go on to the last PC. IP config and DHCP. There you go. It's done. Okay, so the IP configs are done. I will close these PCs down. And then if I go and try to send traffic from here to here, successful, and from here to here, the first packet, as you know, as the drill is, first packet is gonna go fail. All right, so the communication between all the hosts are now done. Now what we want is, we want this particular host to be denied, okay, which is 1.3, which means this host needs to be denied there, okay. So what we do whenever we have a standard access control list, the standard access control list is configured and it has an ID or it has a number between 1 to 99. Your standard access control list can be identified with the number between 1 to 99. So you create an access control list that has a number 10, it gets identified as a standard ACL. Okay, and if you talk about extended one, then the extended access control list is configured with an ID between 100 to 199, anything between 100 to 199. So if you have an access control list 102, that's an extended one. That's how you identify them. Now there is a golden rule that we follow, that standard access control list is configured nearest to the destination router. Okay, an extended access control list is configured nearest to the source. I'm in such a bad habit of writing everything in capital, but yeah, the standard access control list is configured nearest to the destination router, and extended one is configured to the nearest to the source router. Okay, which means that whenever we are trying to send traffic from here to here, then our destination or our nearest to the destination router is this R2. And we're going to configure an IP address, we're going to configure an access control list onto this R2, and we're going to apply it to its interface. So ACL creation is defined into two phases. Phase one is creating an ACL, and second phase is basically applying it. Okay, so you can apply an access control list, one ACL per interface per direction, which means that if you have two interfaces, you have this SE2/0 and you have this FA0/0. So you can apply one access control list for SE2/0 and one access control list for SE2/0 and FA0/0, going outbound and going inbound. So this is out and this is in. Whenever the traffic goes inside of that interface, we call it as inbound. And whenever the traffic is going out of that interface, we call it as outbound. Make sense? That's direction. So you can configure one access control list per interface per direction. Do you understand this? Perfect. Now we're gonna configure the access control list here by going on to the R2, and then there you go. I am on R2 and I'm gonna say access list, and then you can check that if you have your access control list between 1 to 99, it's an IP standard access control list, and 100 to 199 is extended access control list. So I would say access list 10, let's say. Then the next option is to select whether to deny or permit or remark the traffic. We only use deny and permit. We don't remark the traffic usually. That's just adding an entry or like a remark for network admin there. But yeah, what we are going to do is we need to deny the traffic from 1.3. This is a host that has an IP address of 1.3. So I'm going to say deny the traffic. Okay, and then I have an option to select whom do you want to deny. So I can directly enter the address. I can say any as a keyword, which is going to block everything or anyone that comes apart. And then I have an option to select a single host address. So right now I want to just deny a single host, right? So I'm going to say deny host space. I can enter the IP address of that particular host, and I can say deny host 192.168.1.3, and that's all that you need to actually define. So I'm saying access list 10, create an access list of 10, then say deny a host called 192.168.1.3 there. Okay, and I'm gonna hit enter, and that's how you actually create the access control list. Okay, now here's another thing. What's gonna happen is with every access control list, there is something called implicit deny. If you have not heard about it, implicit deny. And this implicit deny is equivalent to deny any command. And this deny any command is always at the last of the access control list, which means it is a hidden command. And if I say do show access control list, there you go. When I perform a do show access control list, this is the first statement that I have, which is about denying the host that is 192.168.1.1. And then after that, the second statement or the second last statement that you have over here is 10 deny any, which means that the topology is going to consider whenever there is any traffic that comes up, whenever there is going to be a traffic that reaches out onto this interface or this router, the router is going to open up an access control list and like match the incoming traffic with the statements of the access control list. Now we have two statements, right? We have deny 1.3 and we have deny any. And this deny any will always be there upon every access control list. Okay, it's a hidden one. So if the traffic is from 1.3, then it will match up the first access control list and the execution of access control list is going to stop there. It will not go on to the next statement. But if the traffic is sent from 1.2, then the first statement is not going to be matched because the traffic is not coming from 1.3, right? So then it's going to go on to the second statement there, which is a hidden statement that says deny any. Okay. And that's why what we need to do is whenever we have deny statements in our access control list that are being used, we need to add a permit statement with that. Just a minute, guys. I'm getting an important one. Yeah. So that's how actually access control list. So whenever you have deny statements in your access control list, then you actually need to add permit any statement at the end of your access control list, so that whenever there is no traffic or there is no statement that actually matches your access control list, then everything else apart from that is permitted to be communicated. Do you understand what I'm saying here? So what we do over here is go to the router, and then we add a statement that says access list 10, and then we say permit any. And now if I check do show access list, there you go. These are the two statements that we have. And we still have an implicit deny at the last. But that statement is never going to match the deny any statement, because if the first statement doesn't match up the traffic that's incoming, then it's going to match the second traffic anyhow, and it's going to permit that particular traffic for the communication. Okay, so that's why it's not never going to satisfy deny any. Cool. Now, this is one part. This is creating an access control list. Still, you can see that after creating an access control list, the communication between the hosts is being done pretty good there. Right? Successful, successful. Now you need to apply the configuration onto the interface. Okay, and how you do that? Now we have two interfaces. We have SA2/0 and we have FA0/0. On which interface do you actually need to apply the access control list? So here's the thing. As I told you that the standard access control list is applied nearest to the destination. We'll be applying it on FA0/0 of the router. Because if we apply it on SA2/0, and in future if we connect another network over here, let's say with R2, then the host over here will not be able to cross the router, because it's going to filter that particular traffic on the SA2/0 as it enters it. Make sense? So when the traffic is going to send, or when the traffic is going to be sent from here to here, it's going to go out onto the FA0/0, like outwards towards this host. And that's when we filter it out. So that's why we're going to apply it on FA0/0. Do you understand it? Yeah, we go and say we configure it on FA0/0 on outward direction. So we go onto the router, and then we say interface FA0/0, and then we say IP access group 10, and then we say out. Okay, that's exactly how we configure an access control list on an interface. And now if you check, if I send traffic from here to here, it's failed. Okay, I'll again try this. If I send traffic from here to here, it's failed. If I send traffic from here to here, it's successful. Make sense how it works? Right? Yeah. That's exactly how access control list actually works. Go ahead and try this small lab, okay, and see how it works for you. And then we'll move on with the extended access control list. Hey there, I'm back, and let's go ahead and discuss about how extended access controllers can be used. I hope you can hear my voice. Let me share my screen with you all again. All right. So what we are going to do now is we're going to configure the device with an extended access control list here, in which we're going to block certain traffic to be allowed for the communication purpose, but we don't want the like other users. So what we have in this case is I'll remove the standard access controllers that I have. Okay, so I'm going to go on enable conf interface FA0/0, and I say no IP access group 10 and out. Yeah, and then I'm going to say no access list 10. This is how you remove the access control list from the router that already has access controllers configured. And now if I try the communication, it's going to work. There you go. Successful and successful. Make sense? Now what I'm going to do is I'm going to configure an access control list. But before that, our motive is that I'm going to configure a telnet configuration onto this device, okay, onto this router. And then by configuring telnet, we're going to see that if we get able to configure the router, which is R1, from any of these devices. Okay, so Telnet is basically a remote management protocol that you guys might be knowing. Okay, Telnet, SSH, these are all remote management protocols that you can use in order to remotely manage your, you can say, network, or you can remotely manage your network device there. Correct? So what I'm going to do, I'm going to be on R1, and over here, we're going to say, we're going to create an enable password first that actually protects your enable mode. Like you can see directly from user mode, you can go into enable mode, and then there is no authentication that is actually used in order to secure your enable mode. Because anyone who is able to get into the enable mode, he'll be able to go into the config mode as well. So what I'm going to do here is say enable password Cisco, and then I'm going to say line VTY0 space 4 login local and transport input, or I think, yeah, no, line VTY0 space 4 no login local. That's kind of a wrong command. Exit. I'm going to say line VTY0 space 4 login, sorry, password Cisco, and then login, and that's all. So the first command is enable password Cisco, and then you say line with your 0 space 4 password Cisco, and then login. This is how you configure Telnet onto your device. And then by going on to the PC now, what I'm gonna do, I'll go on PC1, go to the desktop section, and then go to the command prompt section, and then I'm gonna say Telnet 192.168.1.1. And when I do that, there you go. It asks for the password, which is Cisco. I type the password. It doesn't prompt or echo back the password. And then as I hit enter, there you go. R1's user mode. And I can say enable. Then the enable password again is Cisco. And then I can say conf t. And over here, I am inside of my router 1. And I can do almost anything over here. Make sense? So that's how you remotely manage the thing. Now, after configuring the telnet onto your R1, do you think would these guys will also be able to telnet to R1? Do you think that? Is it possible? Some says no, some says yes. Let's try. I'll go on PC3 and the desktop and then command prompt. And from PC3, I'm going to say telnet 192.168.1.1. And hit, there you go. You are able to access the router's CLI. That's basically a wrong command that I typed. I say enable and Cisco. There you go. I am inside of that router. So I'm able to access the router CLI by using Telnet from the other devices as well. Now, we can consider that 2.0 is not a known network to R1, right? We did implement dynamic routing, and that's how R1 actually got to know about 192.168.2.0. So you can consider it as this is not a trusted network. Now, in order to configure access control list, what we are intending is only the people from 1.0 network should be able to communicate with R1 for the telnet. I mean that communication from all these four PCs needs to be done successfully, but only people from 1.0 network or only 1.0 endpoints should be able to telnet to R1 and not the other ones. Do you understand the requirement? The communication between all four endpoints needs to be possible, but then only 1.0 computers needs to be able to telnet to R1. So for meeting out such requirement, you need to create an extended access control list. Okay, and in that extended access control list, how it's gonna work is we're gonna configure an extended access control list in a way that access list, and then we can we need to go into config, and then we say access list, and then we specify 101 here. And then after that, because you need to use a number between 100 and 199. So we say 101, then question mark, then we say deny, or let's say permit. And because we are going to only permit a specific network there. And then I'm going to say permit, and then I'm going to select the protocol that I want to permit. So telnet comes under the TCP protocol, right? So I'm going to say permit TCP, and then after that, I'm going to select the source. So I want to allow the entire network there. And then I say TCP allow 192.168.1.0. And then after that, here is again, we use something called wildcard bits that we used into OSPF. Right, so it's, I'm going to use the wildcard mask that I introduced you into discussions of OSPF, and I'm going to say 0000255. That's going to be the wildcard mask of the network. And then we're going to say the destination is going to be host 192.168.1.1. There you go. And so what I'm saying over here is permit TCP packets from 1.0 network to 1.1. Permit TCP packets whose source IP is from 1.0 network and whose destination IP is 1.1 network. And then only allow them for telnet. Okay. So I'm saying equal to telnet. Only permit TCP traffic from 1.0 to 1.1 that the traffic has, like which are going for telnet. Or you can also replace the keyword telnet with the port number called 23, because 23 is the port number for telnet, and you can almost use it for any protocol that you know, that you are aware about the well-known ports. Sounds good? Do you understand the command over here? Yeah. And then when I hit enter button over here, that's how our command is going to work. Now, here's what's going to affect our network. Now, only the communication from 1.0 to 1.1 will be allowed. But how about these hosts? These hosts are not communicating directly onto the R1 by using 1.1. They are reaching out via the serial 2/0 interface. And the serial 2/0 interface is configured with 3.2, right? So they can also raise a telnet request for 3.1, and then they will be able to reach out to telnet. Do you understand that? So that's why we also need to raise an ACL command that actually configures our thing. Oh, did I apply the access control? Ah, okay. I applied it on wrong router. So I'd say no. Access list 101 permit TCP, or you can say no access list 101. Yeah, and then we're gonna apply it. Access list 101 permit TCP 192.168.1.0, and then after that 0000255, and then equal to 23. Oh, okay. Destination is going to be host 192.168.1.1. There you go. And then we're also going to apply it for the same for this a destination host of 3.1 there. Okay, so that it gets blocked onto both of the interfaces. There you go. And then after that, we need to allow the ICMP traffic, which means pings between them needs to be sent successfully. Correct? So that's why we're going to create another statement that says access list 101 permit ICMP, because ping packets uses ICMP protocol. So we say permit ICMP any. Make sense? That's how it's going to work there. Okay? And then after that, this is how we create access control list. Do you have any questions inside how you create access control list here? Or all of these three statements that I created on R1? The first statement is only allowing the traffic to go from 1.1. The second one is only allowing the traffic from 1.0 to 3.1. And then everything apart from that, if that's an ICMP traffic, it will be allowed. Everything apart from that will be denied. And then we're going to apply that particular access control list onto this interface, SE2/0 inside. Okay, so I go and say interface SE2/0 IP access group 101 inside. Just a minute. Yeah, so that's how you actually apply the access control list into the router. And then if you look, or if I go on to PC1, which is this particular PC, and if I try to communicate from here to the telnet by saying ping 192.168.1.1, oh sorry, telnet 192.168.1.1, there you go. I can access that by typing password and then say enable Cisco, and I'm inside of that router. If I break that particular connection, if I try to access it onto the same router by using different IP address, there you go. I'm able to access the same as well. Okay, and take an exit. But if I go on to the PC number 3, which is this PC, and if I try to access the same from here now by saying telnet 192.168.1.1, there you go. It is not able to reach out to that router by using this as well, and by using the other IP address as well. Okay, so the telnet connection is blocked there. But if I see the communication between the hosts, then you can see that ping packet from here to here is actually successfully being delivered. Do you understand how it's working here with the head? That's exactly how extended access control list works. Okay, so go ahead, try this particular lab on. The commands that we have used are IP access. Sorry, the commands that we have used is access list 101 permit TCP 192.168.1.0 host 192.168.1.1 equal to 23. Okay, and then the second command has been for the destination of 3.1, and then after that I have said access list 101 permit ICMP any, and then we went on to the interface SE2/0 and say IP access group 101 in. That's what the commands have been. So go ahead, try this particular lab on and see if it works for you. Okay, and then we'll move on with the next one. All right, guys, I am back here. Now, to discuss a couple of topics that are left now, let me just give me a minute, okay? And there you go. I hope you all can see my screen now. The other screen. Cool. So we are going to discuss about a couple of topics that are there. First one is network address translation. NAT stands for network address translation. So usually what happens, because if we talk about both the network address translation and the IPv6, both of these concepts are related to you can say IPv6 and its or you can say IPv4 addresses running out. So if you look at the IPv4 scheme, or if you look at any of the IPv4 address, then the address looks something like this: 192.168.1.1 or something like that. And this is kind of a 32-bit address. So usually what we had was in IPv4, we only had 2 to the power 32 range of IP address that were about like 1.6 billion addresses or something like that. Oh no, not 1.6 billion, but around 4 billion addresses. And that which is nearly equal to half the population of the world. But in the early like ages of internet that was like actually becoming popular, big companies like Apple, big companies like Cisco, and every other company, they kind of grabbed and purchased the large scale of IP addresses that you had. For example, Apple purchased a range of class A addresses like 10,000, okay, and that would actually reserve them or give them around 2 to the power 24, like these many IP addresses, which is about around 16 million IP addresses. But they don't really have that much of users that are there, right? So when they purchase a class A range, then just like that, the manufacturers of internet started to experience that the number of IP addresses were running out pretty fast, and they would not be left with so much of IP addresses in the near future. And that's what the reality is. Currently, if you want to purchase any IP address, just make that. Yeah, back there. So as I was telling you, that big companies like Apple and every other company try to grab the big pool of IP addresses, and that's why we are currently ran out of total number of IP addresses that we have in today's world, and that's why the evolution of IPv6 actually have been planned. But before that, the companies, or you can say manufacturers, be it IEEE or IETF organizations like these, they try to create a temporary solution with the help of network address translation, right? NAT. And this NAT is something that created a range of, it divided the IPv4 addresses into two parts. Okay. So you have private range and then you have a public range. Now, for every class that you have that is actually usable by public, for example, class A, class B, and class C. Class A, class B, and class C actually can say that there are a set of ranges that are defined for all of these classes. So for class A, you have 10.0.0.0/24, then you have 172.6, sorry, not slash 24, but yeah, 10.0.0.0/8, then you have 172.16.0.0/12, and you have 192.168.0.0/16. These are basically the ranges that actually can be used in order to implement network address translation. So whenever you have a network in a way that has this R1, and then R1 is actually connected with the ISP, and then you have your inside network like this. No matter how big your inside network is, this will be called as inside network, and that will be called as your outside network. So in the inside network, you can have any of this IP address installed, and as soon as the traffic reaches out onto the outside world, the addresses gets converted into public addresses that your ISP allocates. So ISP has the control over the public IP addresses. There is an organization called INA, International Association for Number, or International Authority for Number Assignment, and that organization provides the IP, the public IP address ranges to the registries. Okay, or you can say, yeah, and there are registries that are there which are geographically defined. So if we talk about our registry, then we have APNIC, not epic, but yeah, APNIC, that's there in India. Okay, so if Airtel is one of the popular ISP in India, he wants to purchase a range of IPv4 addresses, then he needs to request towards APNIC. APNIC stands for Asia Pacific. Like you can say, the full form can be checked onto the website of INA. But yeah, APNIC is basically the registry that is responsible for allocating all the IP address in the region of Asia and Pacific. Makes sense? So just like that, you have ARIN, you have RIPE NCC. Okay, then you have some others as well. There are around 5 or 6 registries that are there which geographically allocates IP addresses. So when the ISP requests to the registry, then it gets the block of IP address assigned, and then those IP addresses can be assigned for all the public communication. So whenever you step out of your public network, no, private network, then your IP address is something else. Whenever you step inside your public network, then for internal communication, the IP address is all private. That's exactly how translation can be understood. Now there are also different parts or different type of NATs that exist. One is called as static NAT, where the one-to-one mapping is done, which means if you have 5 private IP address, 1.1, 1.2, 1.3, and like that, then all these private IP address will get 5 public IP address like 200, 111, 1.2, 1.3, 1.4, like that. Makes sense? That's called one-to-one static IP address mapping there. Then the second type of mapping that you have is dynamic, which is quite similar to DHCP, where you will have a pool of IP addresses there, and you can say 1 to 1, but random, not static, which means you have a pool of IP address which are public IP address, and single IP address will be assigned to each of the private requester there. Makes sense? But it's not fixed that which private IP address will get what public IP. That's not fixed there. So both of these methods are not PAT, port address translation. Okay, or you can say, yeah, port address translation is exactly what we use. And this port address translation can actually be used in a way that you can actually assign multiple private IP addresses. So this can be around 60,000 private IPs can just be assigned to one public IP. You get that? What I'm saying is 60,000 private IP addresses can actually be assigned to one public IP. Am I audible? I hope I'm audible there now. Yeah. So I'm saying that 60,000 private IP addresses can actually be assigned to one public IP address. Okay, and this is exactly how network address translation works there. Make sense what I'm talking about? Now, there is not specifically any lab that actually can be done, but what I can say is the classification of the IP addresses can actually be done. Yeah. So if I talk about the classification of how it actually is done, then port address translation is basically something that, so public IP address is very expensive. Okay, it is and it's kind of a resource that you can say which is about to end, which already has ended. Okay, the last public IP address was purchased in 2013 by a company in China. So what happens is if you have your R1, this is your private network, and then you have around 60,000 users. To these 60,000 users, your public IP address, or this is your ISP router, that's going actually 200.1.1.12, let's say. That is actually assigned onto this IP, onto this interface, the WAN interface of your router. So whatever network that you use, be it like 10.0.0.0 network or be it 172 something, whenever these packets actually try to take an exit, they are going to use the source IP address as this, or the IP address that's going to be used is the public IP address, which is assigned onto the WAN interface of your router. And that's what the IP address will be. They will carry throughout for the communication. So no matter where they go onto this WAN internet, the IP address that will be used as a public IP will just be the outside interface one. Do you understand that? And you can like attach almost 60,000 computers with one public IP address. That's what we call as port address translation. How it works is, let's say you have 1.1, 1.2, 1.3, 1.4, 1.5, and all of these addresses are being mapped to single address like this. Then the port number will be different. The port number can be 10, 20, 30, 40. The dynamic port assignment will actually be used. Make sense what I'm saying? Exactly. So that's exactly how it actually works. Okay, the network address translation. And yeah, that's what it is. Okay, give me around that was all that we had to discuss on NAT. Now we'll move on to the IPv6. Just give me around 2 minutes and I'll resume the thing. Yeah, I'm back there. Moving on, we also need to discuss about something called quarterless translation, right? which is pretty much going to be the last topic. So I hope I'm audible and my screen is visible to all of you. All right. IPv6. Simple. So when we actually look at IPv6, then the main reason to start using IPv6 is some features as well along with that, where you don't have any broadcast traffic. Okay, that is kind of, and then you can really can be auto configured. Audio is breaking. This might be the internet issue then. Can you hear me? Is my audio good now? I think when I say is my audio good, then it's all good. When I start speaking, then my audio is not good. Okay, bear with me some time. Otherwise, it will be there in the recording as well. Okay. So as I was telling you, that IPv6 is actually something that was introduced in order to fill up the gaps of IPv4. There were some temporary solutions that were actually implemented, which could you can say allow you to use VLSMs and other features of keeping up with IPv4 for some longer amount of time. But when we talk about IPv6, then IPv6 is actually made up of 128 bits. Okay, which means you can have almost 2 to the power 128 number of, or not 2 to the power. Basically, you have 2 to the power 32. That actually gives you around 4 billion. If I make it 2 to the power 33, that's going to be 8 billion. And you need to keep on doubling the value until unless you reach out to 2 to the power 128. That's how the thing is for IPv. So you can imagine how big the number of IP addresses you can have. It's said like the entire IPv6 address space is around some billion times the size of the complete IPv4 space. So the complete IPv4 address is only 1.2% of the total IP addresses that can be consumed in IPv6. Okay, and yeah, so there is no broadcast traffic. There is auto configuration that your interface can actually automatically configure itself an address, and then you don't have any network address translation need or port address translation needs there. And you can say that there are other features like security is provided and various other things are given there. Now we don't use decimal numbers that we used to have in IPv4 like 192, 168, and something like that. That's not there. IPv6 is completely based on hexadecimal addresses. Okay, and you can say that the address can actually look something like 2041 colon 1234 colon 140F colon 1122 colon A B C D colon E F 12 1 2 3 4 5 6, and then you need to have 8 such octet. So you can say 3 4 5 6 7 8 9 0 or 7 8 9, yeah, 0, like that. So this is how big an IPv6 address can actually look like. But there are different techniques. Like now, imagine if you have to call one of your users and one of your IT guy and report this particular IP address. Even you will not remember what IP address you are actually reading there, right? So, in order to remember these IP addresses, there are different techniques how you actually work with it. Okay, which is actually called as shortening of IP v6 addresses. Now, what you can do, if you have an address like this, which starts with 2041 colon 0000 colon, you can say 140F, then colon all zeros, right? And then you have 875B 1312. You have an address like this. So how would you write down the address in the newer form? Now IPv6 address are decimal, as I told you, since they are 128-bit. And so to your understanding or your memory better, IPv6 addresses can be shortened. Okay, and how they can actually be shortened? The zeros can actually be omitted. Yeah, you mentioned it correctly. So if there is a string of zeros, then you can remove them once. Now you can see there are two strings of zeros. You have this and you have this. So you can only remove it once. You cannot remove them both. Now, of course, anyone would choose to remove the number of zeros there. He or she will be choosing to remove the biggest string of zero. So then the output of such kind of IPv6 address after shortening it becomes 2041 colon 0000 colon 140F colon, and then you will need to mention again the colon, and then you can say 875B colon 1312. That's exactly how you can make that particular thing. And then again, if you even now want to make it even smaller, then what you can do is you can replace the four zeros with just one zero. So you can say 2041 colon 0 colon 140F colon colon 875B colon 1312. That's how short your address can actually be. So there's the total number of sections that you need to have are 8. Now your IP has 1, 2, 3, 4, and 5. So what the computer does is it assumes as 5 sections are 3 sections of zeros inside. You understand that what I'm saying? That's how IPv6 actually IPv6 addresses are shortened. And then there is another way of how you can yeah. So that's how IP addresses can actually be shortened. There is another way how you can shorten down the IP address. Like if your IP address is something like this, 2001 colon 0001 colon 0002 colon 0003. Like that, the IP address can be said written like this 2001, and you can remove the leading zeros that you have inside your section. So you can write it as colon 1 colon 2 colon 3. Make sense what I'm talking about? That's another way of how actually the thing can be assumed, and that's how IPv6 addresses are used. However, in order to understand how you configure them and how you like assign them to addresses and all that, there's no lab in IP in the CCNA section. But yeah, the routing and switching can also be done by using IPv6 addresses, and about that, the documentation will soon be shared with you all. But this is what I had to introduce to you guys, and I think my internet is making issue now. There is another actually connection being installed in my house right now, but yeah, I'm getting rid of my previous connection as it's no longer stable now. But anyways, that was basically the topic that I had to discuss about IPv6 and about NAT, and I hope you understood the short introduction to how they actually work and how they can be understood in a way. However, uh, you can see that if we look at the content of the entire CCNA, then we have covered almost everything there are some parts of like small topics like ether channels and an introduction to VTP and some section of security where the introduction of VPN and port security and others are done. But we were actually running pretty short on time because I have some other commitments that have came up and I need to get done with it. But I'm going to share some material with you that would actually help you in order to complete your CCNA studies. And I have made sure that whatever requirements are there that actually needs to be completed by using or by demonstrating the labs are clear or are covered. And whatever topics are left, you can just study them by yourself as well. Okay. Or I am also planning on my videos of CCNA video series. So you'll be getting those my CCNA recorded video series in pretty soon there as well, and you can revise from that as well. Okay, so I can say that that was actually all that we had to discuss. The automation and programmability. I have shared a recorded video of my webinar as well, right? So I've covered everything of automation and programmability that we had to talk about. And you can watch the recording. That's the entire thing that is covered into the CCNA as an introductory part. There is no lab for automation there. So you can watch my recorded video of webinar. And I have also demonstrated the labs there. I guess Amar and Maqsad and Muhammad, you guys were there in my webinar, right? So that's the entire content of CCNA's networking, automation, which is there officially. Make sense? Yeah. And apologies again that I had or I need to actually end up the session before the scheduled time. There were a couple of messages that I saw in the Telegram group that people were saying the class was about to finish on 21st. But I have something that needs to be taken care of next week. Right? So as soon as we get done, yeah, I'm going to post the list of topics that we have covered and the ones that are remaining. Okay, and we're soon going to finish up with the recorded CCNA. So I'm going to share that entire. That will basically come like have every topic that's there into the CCNA. Okay, but this was just a live class that we conducted, and I hope you enjoyed every content of it. I would like to thank you so very much, everyone, for joining up this meetings every weekend. Maybe like you might have not enjoyed most of it or some of it, but yeah, I hope I made sense throughout the session, and the knowledge that I shared with all of you might be some of your help, and it would help you in order to build up your career and knowledge in a better way possible. So that was all. I would say that I would say that was all that we had to discuss in this particular session. And thank you so much, everyone, for hanging in. And looking forward to see you guys in some or the other batches of ours. Okay, I'll be sharing all the links and study materials or the links for that on my Drive link, and I'll share the Drive link into the Telegram group. So keep posting your messages and sharing your thoughts onto your Telegram group. Okay, and I'll be connected over there with you all. Cool. However, I'm posting up, you can say, a message which includes a feedback link and which also includes some other things there. And you need to fill up the feedbacks, and you need to also try and share the posts on your LinkedIn if you can, tagging us so that we know who all attended our trainings. All right, so there you go. You need to fill up the form that I pasted into the chat section. Okay, and so that we can disburse your certifications or your certificates. Cool. Thank you so much, everyone, for joining this session. You'll soon get the recordings of this session as well. And do practice a lot. Reach out to me whenever there are any issues with you, and your feedbacks will be much, much appreciated. Okay, that's what keeps us going so that we can come up with more free batches for all of you guys. Thank you so much, everyone. Take care of yourself. Be safe. Be with your family. And I'm looking forward to see you guys somewhere near future in some other batches of mine. All right. Thank you so much. Take care. Bye-bye. Have a good time. Bye-bye. Thank you.